And there is this live stream also on
Yes,
YouTube right now.
exactly.
Right.
Just for those that want to stay unannounced. So
Yeah, sure. Check.
For those who just join us, we will take just a couple of minutes more to wait for other participants to join us, and then we will start.
Mhm. Ah, hi. So I can answer both in the chat and here via voice.
Yep.
Nice to see you. Oh, your weather looks much better than ours here in Germany at that time of the year.
This is the right time to be in Florida.
Okay, yeah. Maybe it's not the right time in the year to be in Germany, to be honest. Today it's rather nice, but it's already dark outside, so you cannot see anything.
Okay, I think I can introduce you, Martin, and then we can start the seminar. So thank you everyone for joining today for this last episode of an optimal seminar series this semester. So and thank you so much for staying with us all this semester. So today it's our pleasure to host Martin Schmidt. He is with Trier University in Germany. And we know Martin thanks to his contributions as a cross of hierarchical and nonlinear optimization and his applications to electricity and natural gas markets. So Martin, he holds several awards, and among them is a Howard Rosenbrock Prize 2020 award for the best paper published in Journal Optimization and Engineering. And we also know Martin as an associate editor of OR Spectrum and Eurojournal on Computational Optimization and other journals. So you can learn a lot about Martin if you follow him on Twitter, about his academic work, and beyond that, specifically his cooking skills and photography skills. Yes, thank you, Martin, so much for joining us today. So it's a great pleasure. So the stage is yours, please.
Yeah, thank you very much for this very kind introduction. So I hope you're not disappointed that I will not talk about bread making or beer brewing, but only about a multi-level optimization application in electricity market design. So first of all, let me share my screen. So now you should see the slides. And yes. Now you should see them also in full screen. And do you also see my mouse cursor so that I can use
yes.
it as a pointer? Perfect. Okay, yeah. Again, thanks for the invitation. The topic today will be on, as it is written here, multi-level mixed integer nonlinear optimization for electricity market design. And there are a lot of buzzwords in this title that announce that this is a pretty hard optimization problem that we have to deal with. And what I will present today is the outcome of a series of papers out of a project with optimizing guys like I am, and also economists that we worked on with this. And to be honest, at the very beginning, when we started with these projects, and the economists wrote down the problem, and I formalized it a bit, and I came up with these multi-level mixed integer models. I said, well, okay, let's better choose a different topic, because this is by far too hard to be solved. But then we there was a new PhD student, I just sent him to hell, and he came back with some with some nice results. So I'm going to talk about the results of these projects here. Yeah, these are the people who did the work jointly with me. So the PhD student I talked about, this is Thomas here. And well, before these projects, he still had some hair. Afterwards, the hair was gone. And there's also Frauke Liers from Mathematical Optimization in Erlangen, and Gregor Zöttl, Veronika Grimm, and Miriam Ambrosius. They have been the economists with whom we developed the models, and who also helped us a lot in interpreting the results and so on. Okay, by the way, when I now start talking about the content itself, whenever you have any questions, just feel free to interrupt me. So it's better to have the discussion right away. So just unmute or put something in the chat. That's not an issue. Good. So that's the outlook, the agenda of my talk. In the beginning, I will give you some kind of a motivation why we discussed the problem or studied the problem that we then studied. Afterward, I will present you the mixed integer multi-level model. It will be a tri-level model. And then we have some tailored solution approaches. Then I will briefly touch some numerical results that are more important from the computational side, so that you see how hard these problems indeed are. And finally, I will go to a case study for the German electricity market to see what you can really do with our models in practice. Okay. Good. So I have some German newspaper articles, so I will translate the main topics here. So what you see here, when der Strompreis geteilt wird, is like when the price of electricity will be divided. Yeah. So this is a big discussion that we had and have in Germany on whether we should have different price zones for electricity. So right now in Germany, we only have one price for electricity. We call this an energy-only market. So there are no physical constraints, and this mathematically leads to one price for electricity everywhere. This is, for instance, completely different in some parts in the US, where you have nodal pricing schemes, which means that you might have a different price at every node of the network. So it's the complete opposite from nodal pricing. Okay. So due to several reasons, this was and still is in discussion in Germany and in Europe. And here you see the topic, well, will we have 20 different price zones in Germany soon? So also the question on how many price zones shall we have if we decide for such a zonal system is something that is discussed in politics and in the newspapers and so on. So let me introduce why price zones are important from an economic or societal perspective. So the picture that you see here, I mean, this is Germany. Maybe you took already note of it. And well, what I first described is what I call here the old system. So 20 years ago, you had a rather tailored network. You knew where your main demand centers were, and you also had some conventional producers. You can ramp them up. In the past, you were able to ramp them up quickly to react to some changes in the demand profile somewhere in the network. And this was all pretty stable and easy, kind of easy to control, although this, of course, was already a pretty complicated system. You all know that this system changed in the last years, and we have more and more renewable energy in the system. And in Germany, the situation is that we have a bit solar power. I mean, Alexandra just showed us the weather in Florida with a lot of sun right now. This is not the case in Germany, and also in our summer, there is not that much sun. Most of the part that we have as a renewable energy carrier are the offshore wind power farms that we have in mainly in the Northern Sea. There are also some in the Baltic Sea, but mainly in the Northern Sea. Okay. So what this is causing is that we have kind of a north-south bottleneck in our network in Germany. So we have to transport a lot of the power generated in the north to the south, because the south in Germany usually have the larger industrial centers, okay, the larger companies. So the main demand is more located in the south. So you have this, say, transport pattern which is mainly a north-south pattern. And if you think 1 second about how to resolve this problem, you come up with this remedy number 1 here. Well, just build more lines. Sure, this would resolve the problem. However, it's pretty expensive. And it might not really tend towards a better market environment in the end, okay? So, but the main, say, issue with this remedy is that it's really expensive. Building these lines is very expensive. So there is another remedy. If there is a lot of, say, demand in the south, you could have also more power generation in the south. So you could try to go to a system where you have a production that is closer to your demand. However, this production closer to the demand needs to be incentivized, kind of, because the guys who are, I mean, producing the power, they are profit maximizing firms. So they build their power plants where they maximize their profit with in the end. So one incentive, of course, is then to say, well, if we want to have more production in the south, we need higher electricity prices there. And this is the main motivation to discuss this zonal pricing regime, that you don't have only one system where you have one price everywhere, but that you have different prices, and where you want to incentivize investment in production capacity, you need to have higher prices, because the people then earn more if they produce and sell the power. Okay, so this is the main motivation. There is one question already.
Yes, hi, this is Maria Ilic from MIT.
Hi.
Just want to throw in, because we actually did simulate that north-south bottleneck in Europe. There is a third solution, which usually gets really overlooked, and it is, so if you actually simulate this system, you are going to see that part of the reason that you cannot transfer from North Shore down to Bavaria is because you have voltage problems.
Yeah.
Yes, and if you do a little better optimization to support control of the controllable equipment on the transformers and the existing things, just do scheduling of that controllable equipment better. I would love to follow up with you to show you the study that we presented to 50 Hertz on that. Okay, yeah. So just to put the question on the table is, grid should not be only considered as a constraint, but also as an enabler, just to put it on in the context of discussion.
Yeah, thank you very much for this comment. I agree to 100%. I will later on show you what the physical model of transport is, and I will also very much later show you why we are not able to include these more sophisticated physical things up to now. But this is for sure a very reasonable topic of future work to go into such a direction as well. Okay, so the motivation that I just described to you, if you put it a bit more into mathematical terms, is, well, if you are given a number of price zones, let's call this K now, then you could ask, of course, for, well, how should you configure these price zones so that in the end you get the best system result? And with system result, here I mean that the total social welfare of this economic system should be maximized. And of course, we still want to take into account this possible network expansion. So this gives us two very famous discrete optimization problems as further ingredients of our multi-level model that I will show you in a minute. Namely, you have network design problem inside due to the possible network expansion, and you have a graph partitioning problem inside. This is how you decide which node of the network is going to which price zone. okay? And moreover, we don't only want to solve this graph partitioning problem, but we want it with some kind of connectivity condition on top of it, because you want usually price zones that are connected, okay? You don't want some part in the northern part of Germany connected in one price zone to the southern part, okay? So you want to have a connected graph partitioning problem inside. Okay, a bit more on the European or the German market and how it's organized. So this is the timing that I want to discuss with you. So this is the timeline here. At the beginning, we, for instance, as a regulator or a regulatory authority or the state or whatever, we decide now on the specification of these price zones, and we also decide on the network expansion. Okay, this is the first step. The second step in this timing is that the firms who act profit maximizing, they potentially decide upon generation capacity investments, okay? They maybe decide to build some new power plants here or there, or to just increase the capacity of an already built power plant. So these are kind of long to midterm decisions. And then you have here in our model T periods of a spot market trading. So we consider here day ahead markets, where these firms act, of course. And what you have in Germany is a so-called redispatch that you also have every day after the spot market trading. So what is redispatch? This is something that maybe in the US is not known because your market is completely organized in a different way. So as I already told you, in our current system, we have what we call an energy-only market. And this means that no network constraints are considered at all at the trading stage. This means that the trading outcome might be infeasible with respect to the transmission system. So if this is the case, okay, we have some kind of a redispatch. So the traded quantities need to be changed so that after this modification, the transmission system can transport the quantities at the next day. So this is what I tell you here. And I mean, these are these very famous diagrams by economists that explain the entire world. So what is happening, or how is this redispatch organized, at least in Germany? Well, if you consider an energy-only market, you just take the supply curve, you intersect it with the demand curve. This is your equilibrium, okay? Boiled down to a very, very easy setting so that you get the main ideas. So B will be the equilibrium quantity and C is the equilibrium price. But if you now, for instance, have the situation that you can only transport D, which is less than B, well, then the guy who is actually producing or wants to produce B, but now can only produce and sell D, she or he sells less than traded on the market. So he or she pays back. Now, this is not an actual money flow, but like this, you can understand what's going on in this redispatch. Has to pay back this area here, so to say, in terms of money to the TSO, the transmission system operator. And on the other hand, you also have to curtail kind of the demand. So the consumer behind this demand loses some surplus, some benefit. And this is A, B, D, F. And this is what the TSO needs to somehow pay back to the consumer. And since the demand curve always is monotonically decreasing, this redispatch costs something. And in Germany, the system is organized as such. You should organize the redispatch so that these redispatch costs, which is this red triangle here, is minimized. Okay? So this is the system that we are going to consider. And now I will try to give you an idea about the model behind. Okay, and I will also show you here now really the equations so that you see what we are talking about. But this is the bigger picture. So we have 3 levels. It's a Trilevel model. The player at the top level is the regulator or the state, and he maximizes total social welfare by deciding on network expansion decisions, and by solving this graph partitioning problem with connectivity constraints. The idea of these price zones that are outcome of this graph partitioning process is that the interzonal capacities, they will then be reflected within the trading process at the day ahead market. So within the zones, you have, again, an energy only market. But if you go with an arc, with a transmission line from one zone to the other, this capacity, this needs to be satisfied. The trading outcome needs to be feasible with respect to this capacity. Well, now you have duality telling you this might be then binding. And if this is binding, you have kind of a shadow price at the beginning and at the end of the price. So you have a difference there. This is the price difference. And this is how price zones show up then at the result of this trading process. The trading process itself is in the second level. Here, the players are competitive firms. You have consumers, larger consumers now. We are considering this at the large scale, German market. And you have, of course, producers. These producers have generation capacity investment decisions. You have production and demand constraints. You have Kirchhoff's first law on a zonal level. And you have these flow restrictions on a zonal level. This is exactly what I explained to you a second ago. Well, but since you only reflect the capacity constraints that are interzonal in this trading process, there might still be infeasibilities in the trading outcome with respect to the actual transmission system. So in the third level, this is now the TSO who's acting. He is organizing this redispatch process in order to minimize the redispatch costs. We again have production and demand constraints. And our physical model here is a lossless DC power flow model, which is linear. I will talk about why we don't have something more realistic like an AC power flow here. But for those of you who know a bit about multi-level or bilevel optimization, I mean, if we would have an AC power flow here, this would mean that we have a non-convex NP-hard problem in the lower level. And this is usually something that you would like to avoid in bilevel optimization. Good. First level, a bit more down to the details. So we have different trading periods, T. Then we have nodes in the network, N. At every node in the network, we might have a consumer, C. Then you have this inverse demand function. So this integral is the classical gross consumer surplus term that you have to model the surplus or the benefit for the consumers. You subtract production cost, this linear term here. You subtract the mid to long-term investment costs. So this Q bar here will later on be an upper bound for the actual production. So this is your investment decision. Well, and then you have here your network expansion decision. So ZL is a binary variable deciding for the network expansion. So you have some costs for the lines that you build. So this is a classical welfare function. You just have surplus minus all the costs. Okay. Then you have a binary variable here for the lines that you want to build or not. And you have these binary variables that tell you if they are 1, if node N should be part of price zone I. So these are the binary variables for the graph partitioning problem. Here you say every node should exactly be in one price zone. This makes sense. This is part of your partitioning problem. And you could stop here and you have the partitioning problem already written down. However, you have to model this connectivity stuff. You want that two nodes that are in the same price zone, that they are connected in the graph, connected in the sense that you don't have to go through other price zones. Don't read these constraints, okay? I will give you the idea. You can model this using flow constraints, and this is what we do here. I mean, obviously, a graph is connected if you can send from one node in this graph, say 1 unit of flow to every other node in this graph. That's equivalent to the graph being connected. Now replace graph in what I said with price zone. Write this down for all possible price zones, and you have modeled connectivity conditions for these price zones. And this is what you see here. Okay, I'm not going into the details. I mean, this is just a modeling exercise. You can write this down on your own. It takes some time, but this is nothing special. Okay. So what you again have, or in addition have, are these y variables. They are indexed with a line. L is an index for a transmission line. So these model, or they are one if this line connects two different zones. This is what these constraints are doing. And this is what we need in the second level, because this decides on whether you have an interzonal line or not. By the way, I see that there are some questions in the chat.
It's not a question, it's just a comment from Maria. So she referred to the work discussion. Okay. Yeah, but I will assist you if questions arise there.
Okay, perfect. Thank you. So this is the model of the first level. It's a network design problem with some graph partitioning inside and the welfare optimization in the objective. Oops. Second level. It looks in the objective quite the same. You again have welfare maximizing firms now, but you have the spot market outcome. So D spot is the spot market outcome, and Q spot, for instance, is the spot market production. Okay. So this sounds contradictory because I told you before at the second level, we have profit maximizing firms. We make one very important economic assumption here, namely that the market is perfectly competitive. And then you know from your microeconomics 101 class that you have these fundamental theorems of welfare economics, that your market equilibrium outcome is welfare maximal. So all these guys act welfare optimal on the spot market, but only in this assumption, under this assumption. I will comment on possible further extensions later on. Well, and then you have a zonal model of electricity flow. Again, I'm not going into all the details here. I will just give you the main ideas. So what you now do is you take the price zones that you got out of the first level and just take one supernode in your network for each price zone. Aggregate all the demand and production in these supernodes and write down a very simple linear network flow problem on this, say, reduced graph with these, or this price zone graph. Then on these arcs, they are indicated, by the way, if I go one step further, by these YL variables. There you have capacities of the lines. So these are classic big M constraints here. And if not, you have an intrazonal line and you have no constraints at all. So big M, big enough, blah, blah, blah. You know the story. Okay, this is classic modeling. And then you have production is not allowed to be larger than the capacity, demand is always non-negative, all this stuff. Okay, so this is your zonal market model here in the second level. And then in the third level, you have the minimization of redispatch cost. So here you have these cost terms for the consumers. This integral here is the red triangle that I showed you before. Okay, you don't have to understand all these indices here. You just should get the idea. Okay, so you minimize what is the surplus loss for the consumers. And this is what you have to redispatch on the other hand for the producers. So red here always stands for redispatched quantities and spot stands for spot market trading outcome quantities. So this is exactly the cost triangle that I showed you before. And then you again have, I mean, you have flow conservation here for every node now in the network. Now in the redispatch stage, you really consider the entire network, not only the zonal part, not this reduced network. And what you see here is flow on a line equals susceptance times phase angle difference. So here you see this lossless DC power flow model. Then depending on your network design decisions at the very first level, you have some lines inside or not. So you have to activate, we use here big M constraints again, you have to activate physics on arcs if you build them or you don't see these constraints. You have the same for the capacities. This is, for instance, what you see here. And all the rest is, again, production and demand, non-negativity and bounds and so on. So these are the three models of our market design problem. Okay, so you don't have to understand every index, of course. For this, it's by far too complicated, but you should get the main idea. I mean, if you want to know it in detail, you can go to the papers. Okay. This is the overall structure. So you have a tri-level model, and here in the graph on the left, excuse me, on the right-hand side, you have the dependencies. A red arrow means that, for instance, here, the third level is parameterized by integer or binary decisions of the first level. This is, for instance, the network design decisions, because the network design decision influences, of course, the DC power flow network model. I mean, the network itself that I have in level 3. The same holds true here for level 2, which depends on the discrete decisions regarding the zonal configuration of the market taken here in level 1. And the green arrows are indicating dependencies on continuous variables. So this looks pretty interconnected, but if you take a closer look, you see level 1 is the level where all comes together. If you exclude level 1, if you just cut it here, you just have level 2 and level 3, and level 3 depends on level 2. So the redispatch depends on the spot market outcome. And you can solve this how do you call it? One after the other. Okay, sorry, I'm missing the English word. Subsequently, this is what I wanted to say. Okay, and this is the main idea of our Bandus-like solution approach that we will later on sketch. So, but this is not that's not the first that I'm going to highlight a bit. The first one is based on this lemma here that Thomas and I proved in a 2018 paper. Forget about the formal stuff, I give you the idea. The tri-level model that we have is kind of special in the sense that you can reduce it to an equivalent bilevel model. How do you do so? You just move all the stuff from the third level into the first level. Usually, this is not true. This is almost never true in multi-level optimization. You cannot not just move around things between the levels. However, because the objective functions of the third level and of the first level, they are kind of aligned. They point to the same directions, kind of. Okay, their gradients are showing to the same direction. And since the dependency structure is, as I showed you before, this lemma holds true. So you can reduce it to a bilevel optimization problem where in the lower level problem, you only have this spot market stage. And this was a continuous concave maximization problem. So you have KKT conditions, you have a duality theorem. They are not only necessary, but also sufficient. So this is nice. So what you will do is, you take this reduction to a bilevel problem, you do the KKT reformulation, you do the standard big M trick in order to linearize complementarity conditions. You get a single level MIQP in this setting. So this looks nice. Just throw it into Gurobi. This is the first thing that we always do then. But it turns out that's still pretty hard to solve. And I will show you the running times later on. So what we did is, well, let's try to improve this. Let's find some valid inequalities. Let's find some stronger dual bounds. We all did this. Still very hard to solve. I will show you the results later. So we tried to use this decomposition idea that came out of this picture before, where you saw that everything is kind of glued together in level number 1. So let's do some Bandus-like decomposition. So you have a master problem now in our second solution approach, and you have subproblems. The master problem is just the first level problem, where you throw away all the other decisions, the anticipation of the spot market and redispatch outcome, and you only have an estimation of it here with this tau. I mean, this is like standard Bandus or L-shaped method in stochastic two-stage programming, as you know it. You put in here the cost of your first stage decisions. These are the lines that you build and what they cost. You have the network design constraints, you have the graph partition constraints, and these interzonal line indicator constraints. This you all put in your first level. This is a relaxation, like you always have in Bandus, of your overall problem. And you have this set of Bandus-like cutting planes in order to, well, iteratively rebuild the structure that you get by the lower level problems as well, and that you get it in the first level. So this is parameterized here by this set O for optimality cuts, yeah, in Bandus, and this set grows from iteration to iteration. Okay. Then you have the subproblems, and they are just the second and the third level problem. And this is nice now, because if you have all the decisions fixed for the first level, you solve them subsequently. And they are both convex quadratic problems, so this is not the problem. This is super fast. And with the solution of these subproblems, you can then construct these Bandus optimality cuts. And then you iterate. That's the main idea. For those of you who know Bandus a bit better, you might ask, what about feasibility cuts? In Bandus, there are optimality cuts and feasibility cuts. We do not have feasibility cuts here. The reason simply is you can always find a feasible point. The second and third level will never be infeasible. How do you do so? The zero market outcome is always feasible. It may not be the result that we all wish for because we want to cook or bake bread or whatever, and we need some electricity for that. But I mean, it's a feasible solution of this problem. So everything is always feasible, so there are no feasibility cuts in this Bandus-like approach. Okay, these are the cutting planes that we get. Just give me a minute to give you the main idea, and let's skip the technical details. So the first thing is, well, you see that you bound above these outcomes of the second and third level that parameterize the first part of your first level objective function that you want to minimize. So we want to have cutting planes that bound these terms from above. And if you take a closer look at these terms and at these terms and at these terms, you see, ugh, this looks very much like classic no-good cuts, and they are. However, they are a bit pimped, they are a bit improved. And this improvement depends on these factors that you have here. These factors that you have, they stand for upper bounds here. And these cuts are valid if these phi UB star are upper bounds on the overall optimal solution of your Trilevel model. But this you can effectively compute just by taking the so-called high point relaxation in multi-level optimization and solve, or for the more economically oriented people, this is just the integrated plan, the social planner problem, okay? So by this, you solve this once and then you have these factors. And if you do this also with the network design part, you get these things. If you fix the network design and the graph partitioning solution for the last iteration that you have in your master problem, and you solve the remaining social planner problem, you get these terms. And by this, these no good guts get much stronger in practice. Okay. So this is then the Bandus approach. I mean, it's pretty easy. You have a lower bound, you have an upper bound, okay? You have only one initial upper bound cut so that your first Bandus master problem is not unbounded. You solve the master problem, get the solution, parameterize the second level problem, solve it, get the solution, parameterize the third level problem, solve it, get the solution. Check whether you have found a new incumbent. If so, update, add some cuts. Very classic. So how does it work? First of all, does it work? Yes, there is a correctness theorem. So if you have some reasonable assumptions that should hold, but for real world markets, they are always satisfied. So they are kind of technical, but not a problem in practice. Then your algorithm that I just showed you really gets the globally optimal solution of this Trilevel problem if you have one more very important assumption that is satisfying. Namely, your second level solution always needs to have a unique solution. Your second level model always has to have a unique solution. What was the second level? This was the spot market, the trading, the actual market stage. This is super important, but these kind of uniqueness issues are, I would say, the unloved child of applied power market modeling in OR. There are very many papers out there who do not really consider these things. If you have a lower level problem, which does not have a uniqueness property, you have an issue. You have to deal with this issue. So please take care, okay? And I mean, if you take care, at least scientifically speaking, I can tell you, you can at least write also papers on these uniqueness things, okay? So we took this seriously, and here's a whole bunch of papers that we just wrote about uniqueness of market equilibria in different settings, with storages or not, with different physical systems or not, and so on and so forth. Okay, and I mean, all these papers are kind of, maybe I should not let the editors of eDraw, etc. know this. These are kind of auxiliary papers. I mean, we want to solve this overall multi-level model, but to have a correct algorithm, a mathematically provably correct algorithm, you have to take care, okay? Good. So I'm not going into all the details because this is rather technical and the models are complicated. It's important that you get the overall idea, okay? If you're interested, we can discuss all the details later on if I still remember everything, or you can take a look in the papers, of course. So these are the networks that we consider. And now you might have an arrogant smile on all your faces, and it could be understandable also from my point of view. N is the number of nodes, 3, 6, 9, 12. So are we talking about real world systems? For sure not. That's ridiculously small. Lx is the number of existing lines. L new are the potentially new lines that we can build or not. T is the number of time periods. Okay, so this is usually the number of weeks in the year. This is the number of seasons. So these are the interpretations. Anyway, if you do all the KKT reformulation and all the stuff that you have to do for the third line here, you end up with a single level MIQP of that size. Gurobi doesn't like that. So that's, and you have all these big M's and so on. I mean, we also take care there that they are all correctly chosen and that they are provably correct, but it's a pain in the ass. It's really hard to solve. I will show you the running times later on. So these problems, due to their multi-level nature, they are very, very complicated, although on small graphs. So this is the computational setup here. I guess this is more or less standard. We use Python and Gurobi mainly. Yeah, that's it. Good. So here you see the 6-node network. For those of you who are a bit familiar with the electricity power market literature, this is this famous example by Chao and Peck. Very many other papers solve this or use this as a test network kind of. Here's our 9-node network. So you see, we just took the 6-node network from the literature and extended a bit so that you have an idea what are the networks that we are considering here. So these are the results. These are performance profiles now according to Dolan and Moret. And for the KKT transformation, with and without bound tightening and further valid inequalities. You see, if you do all this bound tightening, you get already much better. So in these performance profiles, the more you are to the bottom right, the better you are, right? No, excuse me, exactly the other way around, sorry. The red one is the better one, okay? The one with the bound tightening and with the valid inequalities. Oh, why is this now colored? I mean, okay, you got the point. Next slide. This is what you see for Bandus, okay? The first one is the standard Bandus, where you only need, I showed you two valid inequalities, two Bandus cuts. If you only take the one cut, which we started with, which ensures to you that you are finitely terminating, this is the red curve, the blue curve is the other one. So this also helped. Further valid inequalities, further cutting planes helped. But what about the actual running times? Maybe this is even more interesting. This part here is the 3-node network for 1 zone, 2 zones, 3 zones. Everything's in the milliseconds, trivial, even for this multi-level model. 6-node network, 4 periods. Well, we get here into the seconds. Bandus still is pretty fast. 6 nodes, 52 periods. KKT approach is hitting the time limit of, I guess, 1 hour here. So this is all in the seconds. So 3,600 seconds have been the time limit here. And here you see the drastic difference already between Bandus and KKT transformation, where we are here already half an hour or something, or 20 minutes. It's still in 1 second or less solved here with Bandus. Okay. The 9-node network, almost nothing is solvable with KKT without further valid inequalities. With some further valid inequalities, you're still in the game, but Bandus completely outperforms everything. If you go to 9 networks and more periods of trading, more trading periods, KKT is completely losing control of everything. And also Bandus starts to be not that good anymore, but Bandus with additional cutting planes still can solve all the instances. And a 12-node network here, there also Bandus cannot solve all the instances. Okay, so already rather small instances can be pretty hard to solve. So now about the real world case study. So what is the best price zone configuration in Germany? So what is the answer to the question that these newspaper articles presented at the very beginning? This is the result for Germany with 1 price zone. This is what we right now have. So here you have it's 75 euros per megawatt hour. This is the price that is outcome of our market model here. You have 1 price for entire Germany. And we have, besides some other, also gas, lignite, and combined heat and power, so cogeneration plants here. If the bar goes up, you build more. If the bar goes down, like here, you dismantle capacity. This we also have in the model. You cannot only extend capacities, you can also dismantle something. Okay, if you go to 2 zones, you get exactly what I gave you before as a motivation. You want to incentivize kind of the production in the south so that you do not have these severe bottlenecks from north to south. So your price in the northern part is now 60, and in the lower or in the southern part, you have 77. And here you see also a bit how does the production capacity change. So maybe 2 words regarding this solution. First of all, it's not a green one at all, especially if you take a look at the gas power plants, which are not what we want to have if we strive towards an energy turnaround in our energy markets. Yeah, they are increased in their capacity everywhere in the south. They are rather cheap. Okay, so this is why they can sell their stuff on the market, because if you have these price zones differentiated in Germany, the very cheap renewable power generation is here in the northern sea, in the northern zone. This is why also the price now is very much lower than before, because you have these very cheap, I mean, they almost have variable production cost 0 if they have been built in our models, okay? So the model gives you what you, I think, wanted to see. You can analyze these effects. And then we also said, well, what is if we go to 16 zones? So Germany has 16 federal states. So we said, okay, what if we do 16 zones? What I do not show you here is that the welfare outcome has a rather high jump from 1 zone to 2 zones. This is very significant. I don't have the numbers here, but I mean, it's a model, right? You calibrate it differently, you get different model numbers at the outcome, but it's very significant. If you go from 2 to 16, you do not gain much more in welfare. So if you remember one of the first articles that I showed you, do we really need 20 price zones in Germany? No, I guess 2 are enough. But let's go back to the 2 zones here. We use this for consulting our politicians in Germany. So our Minister for Economic Affairs, he knows the former one. He knows these results. I mean, roughly speaking, and what is the answer of politicians here? Well, every of these federal states has a prime minister. So if you're the minister of Germany for economic affairs and you see, wow, that's great, so much welfare gain just by 2 zones, let's implement it. And we don't have to build all these expensive lines. But what the minister then tells you is, forget about it. I should be the guy now driving here from Berlin to Bavaria and let the prime minister of Bavaria know that his people now should pay almost 20 euros more for power than the guys in the northern part. I mean, that will never be politically feasible in Germany. I mean, in the US, you have a different price everywhere almost in these nodal pricing regimes. But in Germany, we come from a very different point of view. So this is hard to implement in practice. Okay, so if you want to go to the details, here are some of the papers that we have written on it. The first one is where we develop these models mainly. Then we have the Bandus here for the price zones and optimization methods and software. Thomas and I also wrote a paper on the combination of graph partitioning and network design. Then your Bandus cuts change and you can do a bit more. This is in this discrete optimization paper. And the applied real-world case study for Germany, this is the paper here in energy economics from 2020. So I guess you can get the slides later on, or you have the YouTube video, so, or you find it on my website. Okay. So let me wrap up. First of all, I very much like these projects. Why? Well, they are completely interdisciplinary. I learned a lot from all these people from economy and from the economists on theory about welfare theory and how these equilibria form and so on. You have discrete optimization problems. You deal with Bandus, cutting planes. You have graph partitioning, all these things. So all what you like in discrete optimization. And what I like especially, of course, is that you have this multi-level optimization aspect. So I can do a bit of bilevel optimization, which makes me happy as well. And I mean, of course, the instances are small that we can solve, but you really have the impact of these different levels inside of your model. I mean, in power market analysis or in energy system modeling, people very often solve super large LPs up to 2050 on super granular and finely detailed networks, but you do not learn about what are the right incentives for market design out of these things. And the market design is important in the end, because the firms that have to build up this capacity, they are profit maximizing firms. They are not the state. So I think these problems or models really are important to understand what's going on in reality. And as you saw, you have to develop problem-tailored methods, otherwise you have no chance. But I mean, there is a lot of stuff that you can still do. Everything is purely deterministic in our models. Of course, this is not the case. What about uncertainties, stochastic optimization, robust optimization? There's a lot of things that you could incorporate. I said to you that we made this assumption of market power. Well, we made the assumption of perfect competition. What about market power? Of course, you have market power. What about AC power flow? What about unit commitment? So there are very many things that you have to deal with. So I guess I used much more time than I should use. So sorry for that. But with this, I'm done. And I'm happy to take your questions if there are any. Thank you for your time.
Thank you. Thank you, Martin, for this wonderful presentation. We are a bit over time, but I think we can take several questions. So the first one actually by Maria, she dropped a question into chat. So how does zonal prices relate to active grid constraints? I think it was a question to the real life example you showed us with Germany.
Okay, I understood it a bit different. I mean, if you have active grid constraints, so you have, for instance, a trading outcome where one of these interzonal lines, they are saturated. This is the situation where you get different prices. This is just an exercise in more or less convex optimization duality, okay? So this is what happens. If the interzonal lines are not saturated, you will still get one price everywhere, okay? Only if this is binding, only if the capacity is scarce, then you end up with different prices. But I'm not 100% sure whether this
just to clarify, I very often we have intrazonal constraints, intrazonal constraints, and then you can't just look at the tie lines in between the zones.
Yeah, I mean, this is all the intrazonal lines in our zonal pricing regimes. They are not reflected upon the trading stage. So this is why we still have to have, although we switch from energy-only markets to zonal markets, why we have to have a redispatch stage afterward, because we still might have intrazonal infeasibilities in the network. Sure, exactly.
All right, we also have 2 raised hands. So first one from Conlai Buyers. So feel free to unmute yourself, ask your question.
Hi, thanks for the presentation, Martin. So I think this is, an interesting kind of, model to attempt is, but I was curious about some of the more realistic changes that are happening in European markets right now, and if you were thinking about trying to incorporate those. So first would be flow-based market coupling. So it does make that a bit more complicated. The second, though, being this move towards more market-based redispatch as opposed to the regulatory redispatch that's being shown here, which creates debt gaming opportunities and some locational power issues.
Yeah. Thank you very much. These are wonderful questions. The first one, flow-based market coupling. What I showed you here is mainly a model of capacity-based market coupling, what we had before in Europe. This changed, you're right. And the mathematical answer to it simply is, I think it could not be, at least on a mathematical sound basis, be analyzed. The reason is the following. In the second level problem, you would then have not only capacities between the zones, but on this reduced graph, also like a DC power flow model, because this is kind of the flow. This would be an easy realization or an easy modeling of flow-based market coupling. You lose the uniqueness. We have one of these papers here. I can, if you are interested on this, on my please take it serious slide. This one here in EJOR. This shows that you have no uniqueness anymore in your market outcome if you have, for instance, DC power flow. So the algorithms that I showed to you, they wouldn't be correct anymore. You could miss optimal solutions. So it's a much harder problem. Yeah, I don't want to say it's impossible, but people smarter than me, so maybe you should try to solve it. I have no idea right now. The second question was about, give me a hint again.
Sure. The second question is about the transition away from regulatory redispatch to market-based redispatch, such as incorporating into the tertiary reserves market.
Yeah. So the cost-based redispatch that I showed to you has the nice property that firms anticipate that they will not lose or earn money at the redispatch stage because they are compensated for everything. This is nice because then you do not have another game, so to say, on the third level. We tried to analyze this, and there are papers on that. I can also by some of my co-authors here who analyzed it. It's very hard to analyze. I mean, the UK had something before, like a market-based redispatch model, but then you really have again in the third level already non-uniqueness issues, and it's much harder to analyze. We pick here kind of the assumptions that allow us to still do some algorithmic work. Market-based is really hard to analyze. The gaming aspects that enter the stage, then we have no theorems about characterizations of equilibria, etc., so that we can deal with these problems. But would be interesting, but we had to exclude it so far.
Thank you.
All right. We also have a question from Rahman Khoramkhav, please.
Thank you, Martin, for the very interesting talk. I have actually 3 questions. The first one is about why this system is viable, why the system of redispatching can produce feasible solution, because I'm referring to the slide number 8.
Okay.
So yeah, you get an infeasible solution by ignoring the network constraints, and then you somehow adjust to get a feasible solution.
Yeah.
So what if the gap between feasible and infeasible solution is so wide that some parties lose interest to stay in this system?
Okay, can I answer this question before we go to the other ones?
Yes.
Otherwise, I just missed the other ones again. Well, they do not lose interest in participating because in this cost-based redispatch, the firms know that the money that they earn on the market, they will get, because if the redispatched quantities later on will be different, the TSO or the regulator, they will compensate for that. Okay, so this is why it's more or less unimportant for the firm itself what happens on the redispatch. I mean, this is not actually true in reality, but in this model, because you would always get a complete compensation for everything. So this is the first answer. The second answer to the question is, why is this always possible? Well, mathematically speaking, you can just redispatch everything down to 0. This is always feasible with respect to network constraints. This gives you, mathematically speaking, the proof of feasibility of the redispatch stage independent of the spot market outcome.
But in practice, you cannot basically redispatch 0 amount of power because of the demand side, right?
Yes. What we did in the more realistic latest paper is, first of all, we only redispatched the production side. And for this, we implemented some further load shedding costs, because in reality, this does not come for free, kind of, okay? So this is incorporated in the real world case study. And only if a full acting on the production side does not give you a feasible solution, then we allowed in our model to also redispatch consumption. But this is usually something what in Germany you at least don't want to have. You don't want to touch your consumers, okay? So this is why we do it in this order. First production with load shedding cost, and if this does not help at all, then you go to the consumers.
The second question is about the bilevel programming. I'm also interested in bilevel programming. So I wanted to know if this uniqueness issue that arises in multi-level problems is also important in bilevel programming or not?
Yes. So first of all, it's good to hear that you're interested in bilevel optimization. That's good news. Yes, I mean, if you, for instance, think about the bilevel reformulation that I did, where I just move everything from the third stage into the first stage, you have this market stage in the lower level. So this non-uniqueness would translate into a non-unique solution of your lower level problem in the bilevel optimization problem. So this is exactly the issue that you then get. And then you have to deal with optimistic versus pessimistic solutions and how to choose and what is true in reality. And this is a much harder.
Okay, but if we have an optimistic bilevel program, would it still be a problem? I mean, this uniqueness of the solution in the lower level?
Yes. In this case, yes, because even if you take the optimistic solution, you do not necessarily know who is getting what quantities at the spot market trading outcome. Two different situations might be welfare optimal, but they might lead to different situations in the network that you then have to redispatch. So the parameterization of the redispatch model, although you make an optimistic assumption, would change the redispatch, and by this the entire system, because this enters again the first level and influences your zonal configuration decisions. So it's not just saying, well, go for optimistic and everything is fine. No, it's much more important. It's much more severe here.
Okay. My third question is that can this problem or trilevel problem be modeled as a two-level bilevel problem with multiple followers? I mean, we have the state that maximizes the welfare, and until we have the followers, let's say zones, each zone represent the follower problem.
Yeah, I wouldn't say that each zone represents a follower, but that every player represents a follower. I mean, I aggregated everybody here in the market stage, which is allowed due to my assumption of perfect competition. If I have market power, if I have real strategic interaction, then I would have to model this really as a game, as a Nash equilibrium, or even
generalized.
Even harder, it's a generalized Nash equilibrium problem at the lower level. The same as for why not unit commitment? Why not AC power flow? Because it's already hard right now. I mean, you can always extend this, and I would love to see other papers who go this way and extend it, but these are tough problems to be solved.
Okay. Thank you, Martin. Thanks so much.
Yeah, thanks for your questions.
Great. Looks like we exhausted all questions here. Okay. So yeah, I also received a privately question, maybe by accident, on the uniqueness, why it's so important, but I think you just answered this question, Martin. Yes. All right, I think we can thanks Martin again for his excellent presentation, and thanks a lot for participation in this final episode of this fall series. And I look forward to get back to you with updates on the upcoming episodes in the future. So thank you everyone for attending.
Bye-bye, everybody. Merry Christmas and stay healthy. Thanks for the invitation, Vladimir.
Yeah, thank you.